Hi, welcome to Computer Science Explained. In this video, we'll talk about signed binary numbers. Binary numbers can be divided into two groups, unsigned and signed. Unsigned numbers can represent only positive numbers. Signed numbers can represent positive and negative numbers. There are three methods of the signed binary numbers representation: sign magnitude notation, 1's complement, and 2's complement. In unsigned binary numbers, all n bits are used to represent the magnitude of a binary number. 2 times 2 times 2 and so on n times equals 2 to the power of n. So there are 2 to the power of n different variants that can represent 2 to the power of n different numbers. And because the first number is 0, the maximum number is 2 to the power of n minus 1. Thus, using n bits, we can represent unsigned binary numbers from 0 to 2 to the power of n minus 1. For example, for 4 bits, there are 2 to the power of 4, which is 16, different numbers. So numbers from 0 to 15 can be represented using 4 bits. MSB, or the most significant bit, is the bit furthest to the left. LSB, or the least significant bit, is the bit furthest to the right. MSB is used to represent a sign of a number. All other bits are used to represent the magnitude of a number. For example, for an 8-bit number, MSB is used for sign representation, and 7 bits are used for magnitude representation. In all three methods of the signed binary numbers representation, sign magnitude notation, 1's complement and 2's complement, MSB equals 1 for negative numbers and equals 0 for positive numbers. Let's consider sign magnitude notation. This is the simplest and the most intuitive method. We use all the bits except MSB for representing the magnitude, and then use 1 in MSB for negative numbers and 0 in MSB for positive numbers. So values of magnitude bits are the same for positive and negative numbers with the same absolute values. For example, this is number 21, and this is number negative 21. You can see that only MSB is different. All other bits are the same. Another example. This is 64, and this is negative 64. An interesting detail is that we have two different representations of 0, positive 0 and negative 0. Now let's calculate the range of values that can be represented with n bits using sign magnitude notation. So if we have n bits, one MSB bit is used for sign representation and n-1 bits are used for magnitude representation. Thus, we have 2 to the power of n-1 variants of positive numbers. We can represent numbers from positive 0 to 2 to the power of n-1 minus 1. Negative numbers are mirrored, of course including negative 0. So we can represent negative numbers from minus 2 to the power of n-1 minus 1 to negative 0. So total range is from minus 2 to the power of n-1 minus 1 to 2 to the power of n-1 minus 1. For example, for 4-bit sign magnitude notation, we have the range from minus 2 to the power of 4 minus 1 minus 1 to 2 to the power of 4 minus 1 minus 1. After the calculations, we obtain the range from negative 7 to positive 7. Let's write out all the binary numbers of 4 bits in sign magnitude notation. For positive 0, we have 3 zeros in the magnitude bits and 0 in the MSB sign bit. For negative 0, we leave magnitude bits the same and change the MSB sign bit to 1. For 1, we have 0, 0, 1 in the magnitude bits and 0 in the MSB sign bit. We leave magnitude bits the same for -1 and change the MSB sign bit to 1, and so on. Now let's consider 1's complement representation of signed numbers. Like in sign magnitude notation, in 1's complement we also use all the bits except the MSB bit for representing the magnitude, and use 1 in MSB for negative numbers and 0 in MSB for positive numbers. All positive numbers and 0 are absolutely the same in 1's complement notation and in sign magnitude notation. The difference is in the representation of the magnitude bits of negative numbers. To represent a negative number, we need to take all bits of a positive number, including MSB, and invert them. In other words, we need to change all zeros with ones and all ones with zeros. For example, this is number 73 in the 8-bit 1's complement binary number representation. To obtain -73, we invert all bits, including MSB. Now let's take positive 64 and make negative 64. Please pay attention that if we invert all bits of negative number, we will return to the initial positive number. Let's write out all the binary numbers of 4 bits 1's complement representation. Please pay attention that in 1's complement we have 2 zeros, positive 0 and negative 0. Positive 0 is 0, 0, 0, 0. After inverting all bits, we obtain negative 0, which equals 1, 1, 1, 1. 1 is 0, 0, 0, 1. Negative 1 is 1, 1, 1, 0, and so on. MSB of all positive numbers equals 0, and MSB of all negative numbers equals 1. If we compare sign magnitude notation and 1's complement, we can see that all MSBs and magnitude bits of positive numbers are the same, but magnitude bits of negative numbers are different. Also, we can see that 1's complement has the same range as sign magnitude notation, from -2 to the power of n minus 1 minus 1 to 2 to the power of n minus 1 minus 1. Now let's consider 2's complement notation. To obtain 2's complement from 1's complement, we need to shift all negative numbers, including -0, 1 position down. So 0 and positive numbers in 1's complement and in 2's complement are the same. but negative numbers in 2's complement are shifted one position down, in such a way that there is only one zero. The range is from negative 2 to the power of n minus 1 to 2 to the power of n minus 1 minus 1. So 2's complement can store one more negative number. This shift is obtained by adding 1 to each negative number, including negative 0, in 1's complement. For example, this is 8-bit 1's complement of the number negative 37. To obtain 2's complement of this number, we need to add 1. In the next video, we will make a detailed analysis of the 2's complement notation. Thanks for watching, see you next time.